Hi everyone, and welcome back to the good stuff we have been doing. I'm so sorry I've not shown you good mathematics on this page over the last 2 days. Point being that I have to go for my sister's marriage and it's a very long distance journey. 2 days I was sitting in the bus for like 2 days because she lives up north and I'm probably just south, so it's quite far, more like almost 800 kilometers of distance. So it was a long distance, and also I didn't even know if I'm going to come with my microphone or my lights. I just say, well, I have to always keep my mathematics active. I have to show the world the beauty of integrals. So I tried my best, and now I'm here to show you this beautiful integral, because we must always enjoy mathematics. It doesn't matter if it is wedding or if it is whatever. We must enjoy math. So for that enjoyment of mathematics, how do we enjoy for today? Well, for today we're going to enjoy this problem. This is a very classic result and is well-known result. If you even learn complex analysis, probably this is going to be the first thing they teach you, because it's a very classic problem that can be solved easily with residue theorem. But of course, we're not going to use residue theorem here, because why not? Everybody is doing it on YouTube. Many solution is based on residue theorem, but I'm here to present you something different, because I would not have this YouTube channel today if I wanted to show you regular mathematics. This is not a page for regular mathematics. This is a page to show you either really cool integrals or the old integrals, but really cool way to solve them. So please enjoy yourself with me while we try to solve this. And to do that, we're going to use the fact that the series for cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 4 factorial, and so on. Because again, the series for sine of x contain only odd terms, so you have an x minus s cubed over 3 factorial, and then plus x to the 6th over x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and so on. So the series for cosine contain the even denominators, and for sine you have the odd denominators. So basically, cosine of x is the sum as n runs from 0 to infinity of x to, negative 1 to the n x to the n over what? Over 2n factorial. So this is the series for cosine of x, because when n is 0 we recover 1, and when n is 1 we recover 2 at the bottom here, and just x squared at the top. Sorry, okay, x to the 2n, yes, x to the 2n, it will be x to the 2n. So basically, if we plug in the series for cosine of ax, you would have the integral. Let's see if you denote this integral by I here would mean, let's take I would become the integral from 0 to infinity of what? Cosine of ax divided by x squared plus b squared dx. It will be equal to the integral from 0 to infinity of what? You have a 1 over x squared plus b squared, but then instead of cosine of ax, you would have to write the sum as n runs from 0 to infinity of negative 1 to the n, then you have a to the 2n x to the 2n all divided by 2n factorial, then you have your dx. So essentially what we have only done here is to just take out this series, just take out cosine of ax and plug in this series. Now what can we do better? Now what we can do now is to write this as the integral from 0 to no, we can pull out the sum though. So we can pull out the sum. So let's see. We can write this as the sum as n runs from 0 to infinity. Now we pull out all of the things that does not concern x. So we have a negative 1 to the n, then you have a to the 2n, and then you have to divide by 2n factorial. And then the integral from 0 to infinity, then you have an x to the 2n times what? So you have an x squared plus b squared, so dx. So now we are making some progress. So what we're going to do is that we're going to notice that 1 over x squared plus b squared is actually equal to the integral from 0 to infinity of e to the negative t x squared plus b squared dt. Okay, because if you calculate the integral of 0 to infinity of e to the negative at dt, you would have 1 over a. So in this case we are replacing the a by all of this. That is the trick here. So we're going to, and also there are many ways to represent this kind of denominators in terms of e, but the form that suits us today is one we are managing here and trying to use. So basically you would end up with, let's go there, the sum as n runs from 0 to infinity. Now you have a negative 1 to the n, you have a to the 2n, and then you have a 2n factorial, and then you have an integral from 0 to infinity of x to the 2n times what? The integral from 0 to infinity of e to the negative t x squared plus b squared. Then you have dt and dx here. So if we go on further, you would also have the sum as n runs from 0 to infinity of negative 1 to the n, a to the 2n divided by 2n factorial. Now you have the integral from 0 to infinity of x to the times the integral from 0 to infinity. You have an x to the 2n, and you have e to the negative t, let me say x squared times e to the negative t b squared. Then you have dt dx. So now what we're going to do is that we're going to you start with dx before we move on to dt. That's what we're going to try to do now. We're going to do dx before we move on to dt. So in that case now we're going to pull out anything that does not concern x out. So we're going to write this as the sum as n runs from 0 to infinity of what? Negative 1 to the n, a to the 2n divided by 2n factorial. Then you have anything not concerning t is going out. So we have the integral from 0 to infinity of anything not concerning x. So you have e to the negative t b squared. Then the rest will be the integral from 0 to infinity of x to the 2n. Then you have e to the negative t x squared. So you have a dx and then you have a dt. So we are starting with dx first of all. Now how do we handle this in our integral with respect to x? Because we're going to compute everything to be in terms of t. Well, we start with some basic substitution because we need to get rid of the x squared term. So what we do is that we're going to take u, let's see. So we're going to come over to here. We're going to take just u to be x to the second power. Okay, if you do that, you notice that du would be 1 over 2 square, du will be 2s dx. What am I even doing? You can take s, this means that x is square root u, so dx would be 1 over 2 square root of u du. So this dx is going to be replaced by this. But what about x to the 2n? Well, x to the 2n is going to be u to the power of what? U to the power of n. Yeah, u to the power of n power, yes. So, and yes, so you can get to write the sum as n runs from 0 to infinity of negative 1 to the n, and then you have a to the 2n divided by what? Divided by 2n factorial times the integral from 0 to infinity of e to the negative t b squared. And then you have, for this inner integral, you have, again, when everything is still limit, so the integral from 0 to infinity, so you have u to the n, e to the negative t n, then you have times du all divided by twice the square root of u, and then dt again. So I think this is some progress. So essentially you have the integral as n runs from 0 to infinity of what? Negative 1 to the n, a to the 2n divided by 2n factorial. But then over here you have the integral from 0 to infinity of e to the negative t b squared. And then here, let's just say we factor that a half. So you have an half times what? The integral from 0 to infinity of u to the n minus 1 over 2 e to the negative tn, right? Tn or tu? Yeah, e to the negative tu, sorry. E to the negative tu, rather. Tu, then du. And then you have dt as well. I think so. Now, what we're going to do is that we're going to take t, we're going to do something. So, because we know that gamma of z is going to equal the sum from 0 to infinity of t to the power of z minus 1 e to the negative t dt. Okay, that is what is gamma of z. So, but in that gamma of definition, there is only a t here. There is no tu. So what we're going to do is we're going to take z to be tu. So essentially u here would then become z divided by t. So u to the power of n minus half would be z to the power of n minus half, okay, all divided by t to the power of n minus half. So we are going to factor that dt. You will have half times the sum as n runs from 0 to infinity of negative 1 to the n a to the 2n divided by 2n factorial. So you see the progress we're making, times the integral from 0 to infinity. Now we need to pull out, okay, of course, the du would be dt over z, okay. So you need to pull out, okay, let us do it together. Et b squared, then integral from 0 to infinity. Here you have a z over t, so you have a z over t to the power of n minus half. Then you have e to the negative z, e to the negative z, and then you have dz. Okay, wait. dz is equals to the du will be dz over t. So we have a dz divided by t. Okay, yeah. So then everything here is dt. So you will have half times the sum as n runs from 0 to infinity of negative 1 to the n a to the 2n divided by 2n factorial. And for over this side now, you would need to pull out the t. So you have a t to the power of negative n plus half, right? Then you add it with this t to the power of negative 1. So you end up with t to the power of negative n minus half. So which is the integral from 0 to infinity of e to the negative t b squared. Then you have a t n plus half. Okay, so all of them will multiply the integral from 0 to infinity of z to the power of n minus half. Then e to the power of negative z dz. Then you have dt. Now, although after having stopped here, though, you have to notice that by the gamma of this is equal to gamma of n plus half, because that would be integral from 0 to infinity of t to the power of z to the power of, or t to the power of n plus half minus 1, which is n minus half, then e to the power of negative t dt. So this will be gamma of n plus half. So you would have this as to be called half times the sum as n runs from 0 to infinity of what? Of negative 1 to the n a to the 2n divided by 2n factorial times the integral from 0 to infinity of e to the power of negative tb squared times what? Times, you would have wait, this is actually a negative and a negative, so I'm supposed to have gamma of n plus half all divided by t to the power of n plus half. Yeah, I'm supposed to have this dt. So now this would be half times the integral from 0 to, as n runs from 0 to infinity, of negative 1 to the n a to the 2n divided by 2n factorial. Then for this part, you have the integral from 0 to infinity of t to the negative n minus half. Then you have e to the negative tb squared. But then gamma of n plus half is going to be the product of let's see how we can simplify this. The question now is, let me zoom out and see. Okay, the question remains is that how do we simplify gamma of n plus half, like gamma of n plus half? So we're just going to take the product of n, because gamma of n plus 1 equals n factorial. So n plus half minus 1 is just, so you have a 1 over 2 minus 1. So you have n minus half. Then you have n minus n minus 1 over 2 minus 1, n minus 1 third, right? Because you have 1 over 2 minus 1, and then minus 1 over 2 minus 1. Okay, that is the 3. Okay, n minus 3 half. Then you have n minus 5 halves, and then you continue. If you take the product, you find out that this is going to be 2 to the power of n. At the very top, you have a 2n minus 1, a 2n minus 3, and a 2n minus 5, and then you are going to continue because it's going to be n times. Okay, now again, this is more like the 2n minus 1 double factorial divided by 2 to the n. Then if you continue to simplify this, because you can express it in terms of 2n factorial, you are going to end up with, I already did the math here and I wrote it down, so let's check. Let me steal from it. Again, I did not do much, don't want to do heavy math here because I did a long trip and I want to be fast. My sister's wedding is still on and they are in the reception ground, so I just say let me just see if I can record a quick video inside 30 minutes. So they're sharing food, of course, but that is not my interest though. My interest is to come and do some good mathematics. So wait, I think I did it. I could have even been done it by now, but I think checking here is faster. Okay, no, I prepared this. Where is it? Yeah, so this is going to equal 2n factorial at the top, and you have square root of pi. Then you also have at the bottom you have n factorial, and then you have 2 to the 2n, and then you have t to the n plus half. So that is what I prepared. So you have a dt. So I believe that from now we can go smoothly. So again, notice that we don't have to waste time, as this cancel out with this, and then we can pull out the two of these. So you have this is equal to half times the sum as n runs from 0 to infinity of what? You have a negative 1 to the n, so you have a to the 2n divided by what? N factorial 2 to the 2n. So then you have the integral from 0 to infinity of t to the negative n minus half, and then what again? No, what am I doing? Okay, this is what is actually easier, so no need for that, and no need for such things. So yeah, so this is t to the n minus half, and then okay, we have to take our square root of pi. So you have a square root of pi here. Okay, so you have square root of pi here, and then what again? E to the negative t b square dt. Let me see. Okay, so here it seems that doing this is actually faster though. Doing the sum is faster. So what we're going to do, we're going to do the sum. We're going to find the integral from 0 to a, we're going to have square root of pi over 2, integral from 0 to infinity of what? Of e to the negative t b square. Then you're going to take the sum as n runs from 0 to infinity. So first you have negative 1 to the n over n factorial. Then for this case you have a squared over 4 to the n power. Yes. So you have a dt. Notice that this sum here, I think I'm missing something though. What is t to the n minus half? Okay, yeah. We are going to multiply t to the n minus half too, because that would be, so that would be because we only need the t to the n. The t to the half does not concern us, so you have a t to the negative n here. Okay, then t to the half power, this will just become down as a square root of t. Yeah, so t to the n does not concern us, so we have, but this t to the n, we can actually write it as just 4t. So you can write it as 4 divided by t. So in this case you have the t. So this right here would be square root of pi over 2 times integral from 0 to infinity of e to the negative tb squared. Then you would have over square root of t times e to the negative a squared over 4t dt. So you can see we have simplified this problem considerably, because next we could write as square root of pi over 2 integral from 0 to infinity of what? We have t to the negative half, you have e to the negative tb squared, and then plus what? A squared over what? 4t, and then you have dt. So next, now what we're going to do is that we're going to write we're going to get rid of this t to the negative half here by writing u as square root of t. So basically u squared, or du would be 1 over 2 square root of t dt. Okay, so t would be equals to u squared, and the limit of integration will remain unchanged. So we write this as square root of pi du will be, okay, that will be, this will be 2. Okay, we don't have to write the half, so square root of pi goes off, so you have the integral from 0 to infinity of what? This will be e to the power of negative u squared b squared plus a squared over 4u squared times du. Now notice that here you could write this as ub, then you have plus a over 2u all squared, because if you take the square you have u squared b squared plus okay, we don't need to write wait. If we take this square, we multiply everything by 2. So okay, we need to write down a b here, right? No, we don't really have to. Let's just say if you multiply them, the u cancel out, so you have an ab, and if you square, you have an a square over 4u squared. So basically we can write this as u squared plus b squared. So we can write this as, let's just write it, it will not be too hard to do. It will write this as square root of pi. So you have the integral from 0 to infinity of what? E to the negative. So first off, you write ub, then you have, you can write minus, even minus work, minus a over 2u all squared, then you have plus ab, yeah, and then this will be the u. So you have square root of pi e to the negative ab, and integral from 0 to infinity of what? E to the negative ub minus a over 2u all squared du. Now if you use the so-called Cauchy-Schonmitz theorem, the one I proved, the link is in the description. We already say the integral from negative infinity from 0 to infinity of f of ax minus b over x all squared dx is 1 over a integral from 0 to infinity of f of x squared dx. So if we use that theorem, this will be square root of pi e to negative ab times integral from 0 to infinity of e to the negative u squared du, and this is square root of pi e to the negative ab times what? Square root of pi over 2, because this is when this is okay, this is 1 over b over 2b. So this is Gaussian integral, so this will be pi e to the negative ab all divided by 2b, so which is what we wanted to prove. And if you miss this Cauchy-Schonmitz theorem, if you don't get it, please check the description. I already established this result, not too long, probably 5 minutes video or 6 minutes video, and you enjoy yourself. A very good proof for that. But you can see that, okay, let's zoom out a bit. The math is already done, and we were able to, of course, get all of this out and complete solution. So thank you very much. I have to end this recording now so I can go out and go to the reception and everybody's dancing now. So thank you very much, and please subscribe to the channel. Bye.